Hi, I'm Sanaz Rastjoo. This is my project for the Solid State course at the Technical University of Graz. I'm going to talk about SEMs. First, I would like to say a short introduction about electron microscopes. An electron microscope is a type of microscope that uses an electron beam to illuminate a specimen and produce a magnified image. An electron microscope has greater resolving power than a light optical microscope and can reveal the structure of smaller objects because electrons have wavelengths about 100,000 times shorter than visible light photons. The electron microscope uses electrostatic and electromagnetic lenses to control the electron beam and focus it to form an image. They can achieve better than 50 pm resolution and magnifications of up to about 10 million times, whereas ordinary non-confocal light microscopes are limited by diffraction to about 200 nanometer resolution and useful magnifications below 2000 times. I can begin to explain what an SEM is. Scanning electron microscope is a type of electron microscope that produces images of a sample by scanning it with a focused beam of electrons. The electrons interact with electrons in the sample, producing various signals that can be detected and that contain information about the sample's surface topography and composition. Before I start to explain more about the technical details of an SEM, let me tell a brief story. An account of the early history of SEM has been presented by Macmillan. Although McNaught produced a photo with a 50 millimeter object field with showing channeling contrast by the use of an electron beam scanner, it was Manfred von Ardenne who in 1937 invented a true microscope with a high magnification by scanning a very small raster with a demagnified and finally focused electron beam. Further work was reported by Swarykin's group, followed by the Cambridge groups in the 1950s and early 1960s, headed by Charles Utley, all of which finally led to the marketing of the first commercial instrument by Cambridge Scientific Instrument Company as the stereo scan in 1965. There are various types of SEMs. One of them is conventional scanning electron microscope. This is the most common type of SEM. It requires a dry conductive sample, often achieved by applying a thin layer of metal to the surface with a technique called sputtering. The sample must be able to withstand a high vacuum. This type of machine is used for routine imaging using either secondary electrons or backscattered electrons. The other one is variable pressure or low vacuum scanning electron microscope. This type of machine is basically like a conventional SEM, but it can be used to image the surface of non-conductive samples, which means no metal needs to be added to the surface of such samples. It is particularly useful for viewing polymers, biological samples, particulate samples, geological materials, and museum samples that cannot be changed in any way. Imaging uses backscattered electrons. The next one is cryo-SEMs. Cryo stands for frozen. A cryoscanning electron microscope is a conventional SEM that has been fitted with specific equipment that allows samples to be viewed in the frozen state. This is especially useful for directly viewing red samples, delicate biological samples, food, biofilms, and nanoparticles. It is imaged using either secondary electrons or backscatter electrons. Another type of SEM is environmental scanning electron microscope. This machine is designed to view a sample in its natural state without the need of desiccation. Some examples of experiments that can be undertaken in the ESEM include the determination and imaging of melting dynamics for physical science materials and determination of crystallization dynamics. There is another method which is called FIB. This technology involves using ion beam directed onto a hard sample. The beam is focused to an extremely fine probe size onto the surface of a specimen. FIB can cut 10 nanometer thin, thick sections from very hard materials. These sections can be taken off as sequential sections, each viewed in turn with the SEM mode, and this imaging information used to construct a 3D image. Machines can have both ion and electron columns on a single instrument called dual beam instruments. The advantage of dual beam machines is that they allow specimens to be imaged in details using the electron beam without damaging the surface of the specimen with the ion beam. And at last, there is electron beam lithography. EBL is a maskless lithography technique used for patterning of computer-generated layout structures on photoresist on Si wafers. To date, EBL remains the highest resolution patterning tool in lithography. It is widely used in photomask fabrication and low volume production of semiconductor components. Now let's talk about the structure of an SEM. It is made of a source of the electron beam which is accelerated down the column, a series of lenses which act to control the diameter of the beam as well as to focus the beam on the specimen, a series of apertures which the beam passes through and which affect properties of that beam. Controls for specimen position and orientation. An area of beam that generates several types of signals that can be detected and processed to produce an image or spectra, and all of the above maintained at high vacuum levels. Now let's see how it works. How does SEM work actually? A beam of electrons is generated in the electron gun, located at the top of the column where a filament is located. The most common used filament is tungsten hairpin gun. This filament is a loop of tungsten which functions as the cathode. A voltage is applied to the loop, causing it to heat up. The anode, which is positive with respect to the filament, forms powerful attractive forces for electrons. This causes electrons to accelerate toward the anode. This beam is attracted to the anode. Condensed by one or two condenser lens and focused as a very fine point onto the sample by the objective lens. The beam passes through pairs of scanning coils or pairs of deflector plates in the electron optical column. The scan coils are energized and create a magnetic field which deflect beam horizontally and vertically so that it scans in a raster fashion over a rectangular area of the sample surface. When the primary electron beam interacts with the sample, the electrons lose energy by repeated scattering and absorption within a teardrop-shaped volume of the specimen known as the interaction volume, which extends from less than 100 nanometer to around 5 micromillimeter into the surface. The size of the interaction volume depends on the electron's landing energy, the atomic number of the specimen, and the specimen's density. The energy exchange between the electron beam and the sample results in the emission of electrons and electromagnetic radiation, which can be detected to produce an image. Let's take a look at different types of signals produced by an SEM. The types of signals produced by an SEM include secondary electrons, backscattered electrons, characteristic X-ray, light, specimen current, and transmitted electrons. Secondary electron detectors are standard equipment in all SEMs, but it is rare that a single machine would have detectors for all possible signals. Backscattered electrons are beam electrons that are reflected from the sample by elastic scattering. BSE are often used in analytical SEM along with the spectra made from the characteristic X-rays. Because the intensity of the BSE signals is strongly related to the atomic number of the specimen. BSE images can provide information about the distribution of different elements in the sample. Characteristic X-rays are emitted when the electron beam removes an inner shell electron from the sample, causing a higher energy electron to fill the shell and release energy. The characteristic X-rays are used to identify the composition and measure the abundance of elements in the sample. That we want to use an SEM, we have to prepare our sample. Before we start preparation of our sample, we need to make sure we know exactly what information we intend to get during the SEM evaluation. For SEM, a specimen is normally required to be completely dry since the specimen chamber is at high vacuum. Hard dry materials such as wood, bone, feathers, dried insects, or shells can be examined with little further treatment, but living cells and tissues and whole soft-bodied organisms usually require chemical fixation to preserve and stabilize their structure. Fixation is usually performed by incubation in a solution of a buffered chemical fixation, such as glutaraldehyde. Coating. Most samples will need to be coated to make them conductive. Carbon is the most common coating material because it is cheap and almost invisible to most X-rays. Gold or gold palladium is preferred if the sample has a very irregular surface and you are absolutely certain you will not need compositional analysis. Now I touch just a few words about resolution of the SEM. Magnification is not the only important feature of an SEM image, but also a high image resolution is necessary. The spatial resolution of the SEM depends on the size of the electron spot, which in turn depends on both the wavelengths of the electrons and the electron optical system and produces the scanning beam. The resolution is also limited by the size of the interaction volume or the extent to which the material interacts with the electron beam. The spot size and the interaction volume are both large compared to the distances between atoms. So the resolution of the SN is not high enough to image individual atoms. Color. The most common configuration for an SEM produces a single value per pixel, with the results usually rendered as black and white images. However, often these images are then colorized through the use of feature detection software or simply by hand editing using a graphics editor. This is usually for aesthetic effects or for clarifying structure and generally does not add information about the specimen. 3D in SEM. 3D data can be measured in the SEM with different methods such as photogrammetry, photometric stereo, inverse reconstruction using electron material interactive models. X-ray microanalysis. X-rays, which are produced by the interaction of electrons with the sample, may also be detected in an SEM equipped for energy dispersive X-ray spectroscopy or wavelength dispersive X-ray spectroscopy. In this presentation, I want to mention some of the advantages and disadvantages of SEMs. Advantages of a SEM electron microscope include its wide array of application, the detailed three-dimensional and topographical imaging, and the versatile information garnered from different detectors. SEMs are also easy to operate with the proper training and advances in computer technology and associated software make operation user-friendly. This instrument works fast, often completing SEI, BSE, and EDS analysis in less than 5 minutes. In addition, the technological advances in modern SEMs allow for the generation of data in digital form. Although our samples must be prepared before placed in vacuum chamber, most SEM samples require minimal preparation actions. Disadvantages. The disadvantages of a scanning electron microscope start with the size and cost. SEMs are expensive, large, and must be housed in an area free of possible electric, magnetic, or vibration interference. Maintenance involves keeping a steady voltage, currents to electromagnetic coils, and circulation of cool water. Special training is required to operate an SEM as well as prepare samples. The preparation of samples can result in artifacts. The negative impact can be minimized with knowledgeable, experienced researchers being able to identify artifacts from actual data as well as preparation skill. There is no absolute way to eliminate or identify all potential artifacts. In addition, SEMs are limited to solid, inorganic samples small enough to fit inside the vacuum chamber that can handle moderate vacuum pressure. Finally, SEMs carry small risk of radiation exposure associated with the electrons that scatter from beneath the sample surface. The sample chamber is designed to prevent any electrical and magnetic interference, which should eliminate the chance of radiation escaping the chamber. Even though the risk is minimal, ACM operators and researchers are advised to observe safety precautions. Although ACMs are large, expensive pieces of equipment, they remain popular among researchers due to their wide range of applications and capabilities, including the high resolution, three-dimensional, detailed image they produce. This is a number of different types of SEM in the Technical University of Graz, which you can find in the address below. Thanks for watching.